Okay, so now that we've looked at the sampling distribution for the difference of proportions, let's talk about estimating the true population proportion difference. So we're still going to keep the same acronym here. Oh, that was a close one. We're still going to panic when we're asked to construct this interval. And now what I'm looking for here is P1 minus P2. I'm looking at the true difference of the population proportions. Now, of course, I can only find the true difference if I actually have these two population proportions, so P1 and P2. And of course, obviously, try to include a variable in context. Don't just put P1 and P2. Put PW if it's for something dealing with west, or PN if it's dealing with north. Who knows? But just try to include that context point in there. Stated random, right? It's still either an SRS or random assignment. Independent, 10% if sampling without replacement. Essentially, P1 has no influence on P2, and it can be stated as two independent simple random samples, and then that would take care of your independent and your random condition. And then lastly, approximately normal by large counts, and we have to check both populations separately here. If conditions are met, we will use a 2-sample z interval for the difference of proportions, which looks something like this bad boy here. We look at the difference, and then we look at their spread or the standard error of the statistic, and then we would be C% confident that the interval captures the true population proportion difference of insert here. So again, here's some interpretations of the interval and the level. And now we are also adding this new layer to it, essentially justifying a claim based on said interval. Now, if I have this confidence interval, let's say something like so. I have this confidence interval, and let's say here's A, here's B. Let's say 0 is in there. Well, the only way that I can get, if I'm looking at the difference here, right, P1 minus P2, and let's say this is P1, let's say this is P2. The only way that A minus B can be 0 would be if A equals B. And if they're equal, there actually is no difference, right? It's included in the interval as a plausible value, meaning it doesn't support the claim that there is a difference. Now, if P1 minus P2 is a positive difference, well, we know P1 is greater than P2. And lastly, if there's a negative difference, then we know that P1 is less than P2. So based on the interval and the signs of the interval, we can conclude some things about the difference in the population proportions. Are they equal? Is one greater than the other or less than? So let's go ahead and take a look at an example of what this might look like. So suppose there are students who identify as female or students who identify as male that are more likely to attend college outside their home state. In order to find out, random samples of both groups for college-bound high school seniors were taken in DFW, the metropolitan area. In September, following their high school graduations, the students in the sample were contacted to see if they were attending college in Texas or outside of Texas, and the following results were obtained. So we have those who are attending college outside, and then those who are attending college inside. Now, it's a two-way table. So I'm going to tally these up, and the total number of female students came out to 450, and the total number of male students comes out to 306. So this is our total column. Okay, so now based on this, we can construct some information to guesstimate this true population proportion difference. So we are going to do the following. We're going to panic. So we need to, first and foremost, we need to find the parameters here. So I'm just going to use the following notation. I'm going to say PF will be the true population proportion of females who will attend college outside of Texas. And then I'm going to let PM be the true population proportion of males who attend college outside of Texas. So I'm actually, sorry, I can cheat a little here. You all got to write it out, but I've already done my time. Oh, and look, it didn't even work. PM. There we go. All right, so I've got my two parameters here that are listed. So I have PF and I have PM. And so I'm looking here for the difference in population proportions for those who are attending college outside of Texas. Construct or interpret. That is what they wanted, right? Following our... Oh yeah, are they more likely to attend college outside? Okay, just checking. I was like, wait a second, I'm making something up here. So for us, we are just going to do PF minus PM. And no particular rhyme or reason. Sometimes in the problem statement, it will tell you what the order is for subtraction. But if it doesn't tell you, just go in chronological order. So we're going to look at PF minus PM, which would be this here. So we're going to look at the population proportion difference between the female students and the male students. Well, next up is we have to check the assumptions. We have to make sure this is a valid inference procedure. So between our two parameters here, we have 4 assumptions to check. Now with the assumptions, the first one is that we were told that random samples of both groups were selected as stated in the problem. Next up, since we are sampling without replacement, right, once we ask one person, ideally we're not going to ask them a second time. We've already got them in the sample. So we are going to use the 10% condition here since we're sampling. So we are going to say we can assume there are at least 4,500 female students in the state of Texas and at least 3,060 students, male students, in the state of Texas. Or you can say we can assume there are at least 4,500 females and 3,060 male from the respective populations from which we are sampling. But there's our 10% condition. Next up, we can assume the results of the female group have no influence on the results of the male students' responses. Okay, so we can assume I'm going to change this up a little. We can assume the responses of the female students have no influence on the results of the male responses. And then last one that we have to check is the normal model. And as you can see by our frequency table, none of those observations are less than 10. So we can say the normal model is appropriate by large counts for both populations. Now, again, I have to show this step here. I can't just claim it. Normally, though, yes, we know that they're not going to give you conditions that won't be met. They might ask you variation of those conditions, but more often than not, for your inference question, you should be prepared to justify each of these conditions. So notice, right, each of these are in context. Granted, the random samples I could have included, like random samples of 450 females and blah, 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 blah. But the context is pretty much in the rest of these conditions. So let's check now N1. And actually, no, and female times P hat of the females. And remember, now since I'm trying to guesstimate, I don't actually know the parameter. I'm just guessing what it is. So when I check my assumptions, I'm checking with respect to the sample. So here I had 450 total females, and then we had the 121 out of these 450, which would produce a result of 121 here, definitely greater than or equal to 10. And we also need to check the failure condition. And honestly, you can pull these from the table as long as they have, I've communicated at least the first one, so at least the reader knows like where I'm getting this number. And then I'm going to check the same for the male students. So I'm going to do it at least once so the reader knows, oh, this guy knows what he's doing. So 306, and of those 306, 94 said they would attend outside. So that is going to be greater than or equal to 10. And then again, notation and the failure condition, that leaves me with 212. So I at least show one of them for both populations so that the reader knows where I'm getting this from. If you just want to be safe and write it all out, by all means, I'm not going to stop you from being a proper statistician. Now we see that we have random samples. They are independent. We're sampling no more than 10% of the populations, and they're approximately normal. Now, since we have this, we're going to spice it up a little, and we're going to say the following. Since conditions are met, we will use, well, now we're not dealing with one sample, but we're dealing with a 2-sample Z interval for the difference of proportions. And then I'm just going to write my key out here. I'm looking at the difference between the proportion of female students and the proportion of male students. So again, how many samples, Z or T, and what is it for? So here, a 2-sample Z interval for the difference of proportions between male and female students. Now that we've got that going, we can actually do a little bit of the math here. And again, we're just going to go into our calculator, and we are going to select the option that says a 2-proportion Z interval, option B in your calculator. And we're going to write out our formula, and we're going to write in our arguments. So in the difference here, we would take the difference between the samples, and again, context, I got to stay consistent. I can't do P1 and P2 if I up here already stated my parameters in terms of female and male students. It's going to be plus or minus Z star, and then we're going to plug in the samples, and I said the P word, I'm sorry, we're going to substitute in our sample statistics here. Since we already named the test, technically we don't have to write out the formula, but I just do this because it looks nicer. I can at least communicate that I know the name and I know what's happening. So here we know that the proportion of female students, which was the successes over the total for the females, so that'll take care of the first few arguments. The successes would have been 121 out of 450. And then the successes for the males, so the success for the male over the sample size of the males here would have been 94 out of 306. And then here, since I want, it didn't really specify, oh it did, 95% confidence. So Z of 95 is actually going to be 1.96 here. So I would put all of these arguments into my calculator, and I'd produce the following interval, negative 0.1043 up to 0.0277. So that's our interval there. And now what on earth does that interval mean? Let's go ahead and summarize. Well, we are 95% confident the true population proportion difference between female and male students attending college outside of Texas. Oh my goodness, Texas is between, and then we're just going to re-quote our interval, negative 0.1043 to 0.0277. All right, now some inequality here, right? Some inequality notation is that since there's a negative, right, at some point the males are greater than the females, and then since there's a positive, at some point the proportion of females is greater than the males. Now what's important though is that based on our interval, do we have data that would indicate there is a difference? How would we know? And that would just be back to the interpretation, and we're going to say the following. We're going to say, no, we don't have enough because 0 is in that interval, and the only way we can get 0 is if the two proportions are equal. So we'll say since 0 is a plausible value for the proportion difference, there is not enough evidence to claim that there is a difference between female and male students who plan to attend college outside of Texas. And I'm actually coming up on my 15-minute mark here. We did it. But we're going to panic, and then based on our interval, we're going to justify a claim. So there's some additional practice on the following pages.